April 12, 1943. Kummersdorf Proving Ground, Brandenburg, Germany. A low-silhouetted American tank rolled onto the firing range, its white stars hastily overpainted with black crosses. Test engineers from Warproof 6 prepared their instruments, dynamometers, chronographs, penetration gauges. The captured M4A1 Sherman, seized intact 3 weeks earlier near Kasserine Pass in Tunisia, represented the first complete specimen available for systematic German analysis. Wehrmacht intelligence had classified Allied armor as technologically inferior and operationally rigid. Yet over the next 72 hours, the data recorded at Kummersdorf would contradict every assumption. Engine performance exceeded projections by 33%. Component standardization revealed a manufacturing philosophy Germany had never considered viable. By the time Chief Engineer Karl Decker compiled his final report, the conclusion was unavoidable. America had mastered industrial warfare in ways the Reich had fundamentally misunderstood. The first M4 Shermans reached North Africa in late 1942 with United States and British forces. To the Germans, who fielded Panzer III and IV models upgraded with long-barrel 50mm and 75mm guns, the new tank seemed conventional. German intelligence reports from the Fremde Heere West initially described the Sherman as moderately armed, sturdy but unremarkable. That perception changed after February 1943, when the 10th Panzer Division recovered 2 intact M4A1s following the Battle of Kasserine Pass. The Heereswaffenamt ordered immediate shipment to the Versuchsstelle Kummersdorf, near Luckenwalde, for systematic evaluation. Chief Engineer Dip. L. Ing. Karl Decker supervised the analysis, supported by technical teams from Warproof 6, the department responsible for armored vehicle development. The goal: determine the vehicle's combat worth and manufacturing methods. Through the shattered morning haze of February 22, soldiers of the 10th Panzer Division discovered 2 intact M4A1 Shermans abandoned near a burned-out American supply column in Tunisia's Kasserine Pass. Oberst Rudolf Lang, commanding the division's reconnaissance battalion, walked around the first tank slowly. The vehicle showed no major battle damage. The crew had fled during the night withdrawal. One tank carried full fuel and ammunition. Lang immediately ordered both machines secured and reported to divisional headquarters. Within hours, orders arrived from Berlin: ship the intact specimen to Kummersdorf for complete technical evaluation. The Sherman had arrived in North Africa only 4 months earlier, accompanying Operation Torch. German intelligence files contained scattered reports: medium tank, 75mm gun, gasoline engine, but no comprehensive analysis. Panzer officers who encountered Shermans at Medjez el Bab and Spatler reported mixed results: adequate frontal armor, vulnerable to long-barrel 50mm and 75mm fire at typical combat ranges, but mobile and consistently operational. The captured tank began its journey northward on February 28, aboard a specialized rail transport. By mid-March, it reached the Versuchsstelle Kummersdorf, the Wehrmacht's primary armor testing facility 30 kilometers south of Berlin. Decker received orders to conduct a complete technical breakdown: performance trials, ballistic testing, component analysis, and comparative evaluation against German medium tanks. The expectation within Warproof 6 was clear: document American engineering deficiencies and confirm German technical superiority. Decker's team anticipated finding crude manufacturing, inefficient power transmission, and poor component integration. They prepared test protocols based on the assumption that American industry prioritized quantity over quality. What the data would reveal over the following weeks challenged that framework entirely. By mid-April, engineers disconnected the Sherman's Continental R975C1 radial engine from its mounts and transferred it to the dynamometer stand at Kummersdorf's engine test bay. The air-cooled 9-cylinder design, derived from an aircraft power plant, struck the German team as unconventional for armored vehicles. Wehrmacht doctrine favored inline water-cooled engines like the Maybach HL-120 used in Panzer IV production. Radial engines were heavier, occupied more vertical space, and demanded different cooling solutions. Test protocols began at dawn. The Continental was fired and brought to operating temperature. Load cells measured torque output across the RPM range. At 2400 RPM, the engine's rated maximum dynamometer readings confirmed 400 horsepower at the flywheel. German engineers cross-referenced the figure against the Sherman's combat weight, 30.3 tons fully loaded, power-to-weight ratio calculated to 13.2 horsepower per metric ton. The Maybach HL 120 in the Panzer IV USF G produced 300 horsepower at 3000 RPM. Combat weight for that variant reached 23.6 tons, yielding 12.7 horsepower per ton. The American tank, despite being 28% heavier, delivered marginally superior acceleration characteristics. More significantly, the Continental maintained consistent output across extended run durations, without overheating, a chronic problem in German medium tanks operating in North African summer conditions. Fuel consumption data surprised the evaluation team. At cruising speeds between 20 and 30 km per hour, the Sherman consumed approximately 2.1 litres per kilometre. The Panzer IV, with a smaller engine, consumed 1.9 litres per kilometre under identical conditions. The efficiency gap was narrower than anticipated. American engineers had optimized the powertrain for sustained operational tempo rather than peak performance, accepting slightly higher fuel consumption in exchange for mechanical durability. Documentation from the trials noted another contrast: maintenance accessibility. The Sherman's engine deck could be fully removed in under 90 minutes using standard tools. Engine replacement in field conditions required approximately 4 hours with a trained crew. The Panzer IV's engine bay demanded 6 to 8 hours for comparable work, often requiring specialized equipment unavailable at forward repair depots. In his preliminary notes, Decker wrote, "American design philosophy accepts compromises in theoretical efficiency to achieve practical reliability and rapid field maintenance. This approach contradicts our understanding of optimal engineering, but demonstrates measurable operational advantages." By April 18th, the Continental had completed over 40 hours of continuous operation without mechanical failure. German medium tank engines typically required inspection and adjustment after 25 hours of field use. The pattern was becoming clear. 3 days later, test drivers maneuvered the Sherman across Kummersdorf's broken terrain circuit, a 12-kilometer loop designed to simulate combat conditions with steep grades, ditches, and obstacles. The vertical volute spring suspension appeared crude in engineering drawings, simple bogie assemblies with coil springs, and minimal shock absorption compared to German torsion bar systems. War-proof 6 engineers anticipated poor cross-country performance and rapid component wear. The Sherman completed the first circuit in 43 minutes, maintaining average speeds of 18 km per hour over unimproved ground. A Panzer IV USF G, tested on the same course 3 months earlier, had required 51 minutes. The American tank's wider tracks 420 mm compared to 400 mm distributed weight more effectively, reducing ground pressure and improving traction in soft soil. Over 6 consecutive days, the Sherman logged 847 kilometers across varied terrain without suspension failure. Bogie assemblies showed minimal wear. Springs retained their rated compression characteristics. German engineers noted that the VVSS design, while mechanically simpler than torsion bar systems, proved exceptionally durable under field conditions and required no specialized tools for repair or adjustment. Comparative maintenance logs told a sharper story. Panzer III and IV units operating in Tunisia reported suspension-related breakdowns in approximately 18% of vehicles after every 1,000 kilometers of mixed terrain operation. British and American after-action reports indicated Sherman suspension failures occurred in fewer than 6% of vehicles across equivalent distances. The German reports concluded, American suspension design sacrifices theoretical sophistication for practical endurance and ease of repair. The mobility trials concluded with a high-speed run on paved surfaces. The Sherman reached 42 km per hour on flat road, marginally slower than the Panzer IV's 45 km per hour maximum, but achieved with better acceleration from standstill. Decker's team calculated that in a pursuit or withdrawal scenario, the Sherman's power-to-weight advantage compensated for its slightly lower top speed. One test driver, Obergefreiter Hans Metz, a veteran of Eastern Front armoured operations, provided an informal assessment recorded in trial logs. The American machine handles predictably. It does not fight the driver. In mud or broken ground, it goes where you point it. Our tanks are faster on paper but break down more often in practice. By late April, the accumulated test data contradicted initial assumptions. The Sherman was not a masterpiece of engineering elegance, but it worked consistently, reliably, and with minimal maintenance burden. That realization prompted the next phase of evaluation, understanding not just how the tank performed, but how America built it. And what the engineers discovered in the following weeks would prove even more disturbing than the performance data. Engineers began systematic disassembly of the Sherman's drivetrain in Kummersdorf's technical workshop. The transmission assembly, a controlled differential system manufactured by Spicer, came free in 97 minutes. Decker's team documented every component, gear ratios, bearing specifications, tolerances, materials. What emerged was a pattern invisible in operational testing: extreme standardization. Every major component carried alphanumeric identification codes linked to interchangeability standards. The transmission housing accepted universal mounting points, compatible with multiple engine types. Electrical connectors used consistent gauge and pinout configurations across subsystems. Fasteners followed American Unified Thread standard specifications throughout the vehicle, no custom or proprietary hardware anywhere in the design. German armored vehicles, by contrast, often incorporated manufacturer-specific components. Maybach engines used unique mounting brackets. ZF transmissions required custom tools for servicing. Electrical systems varied between production batches as factories adapted to material shortages. This design heterogeneity maximized theoretical performance, but created logistical nightmares for field maintenance units. The Sherman's standardization extended to welding techniques. Seams showed consistent bead patterns and penetration depth, evidence of controlled production environments and worker training protocols. German tanks from different manufacturers displayed variable weld quality, reflecting workshop traditions rather than industrial standards. Component interchangeability testing confirmed the pattern. Engineers swapped the transmission from the Kummersdorf Sherman with a unit salvaged from a second M4A1 captured near Tunis. Installation required 38 minutes. All systems functioned normally. A similar test with Panzer IV transmissions from different production facilities had failed 6 months earlier, when mounting points didn't align. The vehicles came from factories only 200 kilometers apart. Decker's interim report, dated May 2nd, noted, American production methods prioritize component compatibility over individual optimization. Each part is adequate rather than exceptional, but the system functions reliably because every element integrates predictably. German practice pursues excellence in components, but creates systemic fragility through complexity and variation. The evidence pointed to a manufacturing philosophy fundamentally different from German practice, design for production rather than design for performance. America had accepted small compromises in theoretical capability to achieve massive gains in manufacturing speed, repair simplicity, and logistical efficiency. That same week, intelligence reports from the Eastern Front noted that Soviet units equipped with Lend-Lease Shermans maintained operational readiness rates above 80%, substantially higher than German armoured formations struggling with parts, shortages, and complex maintenance requirements. The implications were becoming impossible to ignore. By early May, the Sherman sat immobile on Kummersdorf's ballistic testing range, positioned broadside at 800 meters. German gunners loaded a Panzergranate 39 armor-piercing round into a 50mm KWK-39, the long-barrel gun equipping late-model Panzer IIIs. The shot rang across the proving ground. Impact, perforation, clean through the hull side at 38-degree obliquity. The 50mm round, travelling at 835 meters per second at impact distance, defeated the Sherman's 38mm side armour decisively. A second test. Frontal armour at 1,000 meters. The same 50mm gun fired at the glacis plate 51mm thickness at 56 degrees from vertical. The round struck, deflected upward, and failed to penetrate. Examination showed deep scoring but no hull breach. At this range and angle, the Sherman's frontal protection equaled a Panzer IV OSF G. Tests continued with 75mm KWK-40 rounds, the main gun of late-production Panzer IVs. At 800 meters, the 75mm Panzer Granit 39/42 penetrated the Sherman's frontal glacis, though not reliably. 3 shots produced 2 penetrations and 1 deflection. At 1200 meters, penetration probability dropped below 40%. The data confirmed what German tank crews already knew from combat reports. Shermans were vulnerable at typical engagement ranges, but not helplessly so. The Sherman's own 75mm M3 gun received similar evaluation. German engineers test-fired captured American ammunition against a Panzer IV frontal plate positioned at 1,000 meters. The M61 armor-piercing round standardized American anti-tank ammunition in 1943 failed to penetrate the Panzer IV's 80mm frontal armor at this distance. At 600 meters, penetration occurred inconsistently. The American gun could defeat German medium tank armor only at close range or against side and rear aspects. Ballistic testing quantified what battlefield experience suggested. Neither the Sherman nor the Panzer IV held decisive firepower advantage at typical combat distances. Both could defeat each other's side armor reliably. Frontal engagements favored whoever fired first or achieved better positioning. The technical parity shifted strategic emphasis to operational factors, numbers, logistics, crew training, and tactical flexibility. One documented figure changed the assessment dramatically: production rates. By May 1943, American factories were manufacturing approximately 1,400 Shermans per month across 11 production facilities. Germany produced roughly 330 Panzer IVs in the same period from 4 main assembly plants. The United States built 4 medium tanks for every German medium tank, and American production was accelerating, while German output stagnated due to material shortages and strategic bombing. Decker's ballistic report concluded, "The Sherman is not individually superior to our medium tanks in armor or firepower, but numerical superiority of 4-to-1 negates technical parity. The enemy accepts adequate performance, achieves it reliably, and delivers it in overwhelming quantity." The pattern repeated itself across every metric. By mid-May, the captured Sherman had operated for 63 days under German control, accumulating 1,847 kilometers of mixed driving conditions at Kummersdorf's endurance testing grounds. Maintenance logs documented every inspection, adjustment, and component replacement. The results contradicted German expectations about American mechanical reliability. The Continental engine required oil changes every 800 kilometers standard procedure. Valve clearances remained within specification throughout testing, requiring no adjustment. The cooling system maintained stable temperatures across ambient conditions ranging from 4 degrees Celsius to 28 degrees. 0 engine failures occurred during the entire evaluation period. Transmission performance remained consistent. The controlled differential system showed minimal wear on gear teeth after nearly 2,000 kilometers. Lubricant analysis detected normal metallic content, no evidence of abnormal friction or component degradation. The drive sprockets and track system required tension adjustment twice, a routine maintenance task completed in under 30 minutes each time. Comparative data from Panzer IV field units painted a different picture. After-action maintenance reports from Tunisia showed that German medium tanks averaged 1 mechanical breakdown, requiring depot-level repair for every 600 to 800 kilometers of operation. Common failures included transmission-bearing seizures, final drive failures, engine overheating, electrical system malfunctions, and suspension component fractures. Wehrmacht armored divisions typically rated 55 to 65% of their tanks as operational at any given time, with the remainder awaiting parts or repairs. British and American maintenance statistics from the same theatre indicated Sherman operational readiness consistently above 75%. Soviet Red Army reports on Lend-Lease Sherman battalions showed even higher availability. Some units maintained 85% operational status throughout sustained operations. The American tank simply broke down less frequently and returned to service faster when it did. The reliability advantage traced directly to design philosophy. German engineers optimized for performance, higher power density, lower weight, sophisticated systems. Each optimization introduced complexity and fragility. American engineers optimized for endurance, generous tolerances, robust components, simple integration. The Sherman was over-engineered for reliability rather than maximized for capability. Material analysis revealed another factor. The Continental engine used cast aluminum components for the crankcase and cylinder heads, materials abundant in American production, but increasingly scarce in German industry by 1943. The transmission housing used forged steel of moderate quality, rather than high-grade alloy steel. American industry accepted slightly heavier components made from common materials, rather than demanding lighter parts from strategic alloys. A maintenance technician at Kummersdorf, Feldwebel Otto Richter, noted in his log, "The American tank is designed for mechanics, not engineers. Everything is accessible, parts are marked clearly. Procedures are simple. A crew can replace the engine in one afternoon with basic tools. Our tanks are better machines, but worse tools for soldiers." By late May, the cumulative test data supported an uncomfortable conclusion. The Sherman's greatest strength was not visible in its specifications. It was the gap between design capability and field performance, a gap that stayed narrow through mechanical simplicity and manufacturing consistency. German tanks looked superior on paper, but failed more often in practice. The question now was whether anyone in Berlin would listen. In early June, Decker presented his preliminary findings to a technical review board at Heereswaffenamt offices in Berlin. The board was chaired by General Major Heinrich Ernst Kniepkamp, head of Warproof 6, and overseer of German armored vehicle development. The conference room held senior engineers from Daimler-Benz, MAN, Henschel, and Krupp, the industrial backbone of German tank production. The presentation lasted 90 minutes. Decker methodically detailed test results, engine performance, mobility characteristics, armor protection, manufacturing methods, maintenance requirements. Each section included comparative data against German vehicles. The board members listened silently as the implications accumulated. One figure dominated the discussion: production efficiency. American factories manufactured a complete Sherman in approximately 10,000 man-hours from raw materials to finished vehicle. This figure included component fabrication, hull assembly, final integration, and acceptance testing. German factories required 13,000 to 15,000 man-hours to produce a Panzer IV, a lighter vehicle with similar crew capacity and comparable armament. The efficiency gap stemmed from manufacturing approach. American assembly plants used progressive production lines adapted from automobile industry practice. Components arrived prefabricated from supplier networks, met standardized specifications, and integrated without custom fitting. Workers specialized in repetitive tasks optimized for speed and consistency. Quality control occurred through statistical sampling rather than individual inspection. German production retained workshop traditions. Skilled craftsmen assembled tanks in bays, fitting components individually, adjusting tolerances, solving problems through expertise rather than standardization. The method produced excellent individual vehicles, but couldn't scale efficiently. Each tank was slightly different. Each required artisan labor that took years to develop. Documents from the meeting recorded Kniepkamp's assessment: "We have built tanks as if constructing precision instruments. The Americans build tanks as if manufacturing locomotives simple, strong, repeatable. In a short war, our method produces better weapons. In a long war, their method produces more weapons. The strategic implication was unavoidable. Germany's 1943 tank production, optimized and expanded, might reach 500 to 600 medium tanks monthly by 1944. American production was projected to exceed 2,500 Shermans monthly by the same period, a 5-to-1 advantage. No amount of individual technical superiority could overcome that numerical gap. Additional intelligence data reinforced the disparity. The United States operated 47 tank production facilities of various capacities. Germany had 11 major armored vehicle plants, several already damaged by Allied bombing. American industry could absorb losses and expand capacity. German industry operated at maximum sustainable output with no reserves. The review board concluded that Germany had mastered tank design but failed to master tank production. The Sherman, while individually unremarkable, represented a production system Germany could not replicate. American industrial capacity, organizational methods, and material resources created a manufacturing advantage that technical innovation alone couldn't counter. One engineer from Daimler-Benz, Dippel, Ing. Werner Oswald, summarized the paradox in a memo dated June 8. We can outdesign them, we cannot outbuild them. In armored warfare, the second fact is more important than the first. By mid-June, the Sherman completed its last test cycle. Total operational distance, 2,214 kilometers. Engine hours, 147. Mechanical failures, 0. Component replacements, none beyond consumables. The vehicle remained fully operational after 3 months of continuous evaluation under conditions deliberately harsher than typical combat use. Decker compiled the final technical report, Heereswaffenamt File 26/43, dated June 22, 1943. The document ran 73 pages with appendices detailing every measurement, test protocol, and comparative analysis. The conclusions section occupied 2 pages. Its core assessment read, "The M4 Sherman medium tank does not represent a significant individual technical advancement over contemporary German armored vehicles. Its armor protection is adequate but not superior. Its armament is effective but not exceptional. Its mobility is good but not extraordinary. However, the Sherman demonstrates a manufacturing and operational philosophy fundamentally different from German practice. American industry has optimized the entire production system design, fabrication, assembly, logistics, and maintenance for maximum output and minimum field support burden. The result is a weapon system that is adequate in every category and superior in none, yet overwhelmingly effective through quantity, reliability, and sustainability." The report identified specific technical elements Germany could potentially adopt: standardized component interfaces, modular assembly methods, simplified maintenance procedures. But Decker noted that implementing these changes would require fundamental restructuring of German industrial practice, standardization of tools, retraining of workers, redesign of existing vehicles, coordination across competing manufacturers. Such changes would temporarily reduce production while providing long-term benefits Germany no longer had time to realize. A supplementary memo attached to the report contained a more direct assessment. The Americans have understood what we have overlooked. The tank is an industrial product, not a workshop creation. We have pursued technical perfection while they have achieved logistical sufficiency. In mechanized warfare of this scale, sufficiency delivered in quantity defeats perfection delivered in scarcity. Intelligence reports appended to the file provided context from other theaters. Soviet factories evacuated east of the Urals were now producing over 1,300 T-34 tanks monthly, using crude but effective assembly methods. Britain manufactured approximately 400 tanks monthly across various types. Combined Allied tank production exceeded 4,000 vehicles monthly by mid-1943. German production across all tank types, medium, heavy, assault guns totaled roughly 850 vehicles monthly. The arithmetic was straightforward and devastating. Even if German tanks achieved kill ratios of 2-1 or 3-1 in combat, and battlefield reports suggested they often did, numerical attrition favored the Allies overwhelmingly. Germany could not replace losses at the rate America and the Soviet Union could generate new production. Field reports from the Eastern Front confirmed the pattern. Soviet armored units, equipped with Lend-Lease Shermans, sustained offensive operations longer than German panzer divisions because they received consistent supply and replacement vehicles. American and British units in North Africa maintained higher operational tempo for the same reasons. German commanders increasingly reported that their tactical successes created no strategic advantage because the enemy simply brought forward more tanks. By late June 1943, the Kummersdorf evaluation had answered its initial question, what were the Sherman's technical capabilities, but revealed a more significant truth. Technical capability mattered less than industrial capacity. Germany could build better tanks, but not enough tanks. America could build adequate tanks in overwhelming numbers. The war would be decided by production, not innovation, and there was nothing Germany could do to change that. 6 months after the Kummersdorf evaluation, German armoured doctrine remained unchanged. The Wehrmacht continued developing heavier, more complex tanks. The Panther, with its sophisticated torsion bar suspension and high-velocity 75mm gun. The Tiger, with 100mm frontal armour and the powerful 88mm KWK-36, both represented engineering excellence. Neither addressed the strategic problem identified in Decker's report. Production data from August 1943 showed the consequences. Germany manufactured 379 tanks and assault guns that month. American factories delivered 1,821 Shermans. Soviet plants produced 1,443 T-34s. The production gap had widened from 4-1 to nearly 8-1 against Germany. Senior German commanders received copies of the Sherman evaluation. Some understood its implications. Generaloberst Heinz Guderian, appointed Inspector General of Armoured Troops in March 1943, advocated for simplified tank designs, optimized for mass production. He proposed standardizing on a single medium tank type, implementing American-style component interchangeability, and converting automotive factories to military production using assembly line methods. The proposals went nowhere. German industry resisted standardization that would eliminate competitive advantages between manufacturers. The Wehrmacht High Command insisted on pursuing qualitative superiority through advanced designs. Albert Speer, Minister of Armaments, focused on maximizing output from existing production methods rather than restructuring the entire system. Strategic bombing of German industrial centers made long-term reorganization increasingly impractical. By autumn 1943, Germany faced a paradox: awareness without action. Military and industrial leadership understood that Allied production advantages would prove decisive. Yet the German war economy could not implement changes necessary to compete. The institutional, industrial, and strategic constraints made adaptation impossible. Meanwhile, Allied production accelerated. In September 1943, American factories achieved 2020 Sherman completions, the first time monthly output exceeded 2,000 units. Soviet T-34 production stabilized above 1,400 units monthly. British tank output increased to 450 units monthly. Combined Allied production reached 3,900 tanks in a single month. German commanders on all fronts reported the same pattern: win battles, lose campaigns. Panzer divisions defeated Allied armoured attacks through superior tactics and gunnery, then withdrew because the enemy brought forward fresh units while German losses could not be replaced. The Eastern Front, North Africa, and soon Italy demonstrated that tactical excellence could not overcome strategic exhaustion. A report from Panzer Army Africa, dated November 2, 1943, summarized the operational reality. Our tanks are better. Their tanks are more numerous. Numbers have become decisive. Each engagement costs us irreplaceable vehicles and trained crews. The enemy replaces losses within days and returns with greater strength. The lesson from Kummersdorf was being written in blood across multiple fronts. On June 7, 1944, the Sherman returned to German consciousness no longer as a test specimen, but as an opponent in overwhelming numbers. Allied forces landing across 5 Normandy beaches brought approximately 2,000 armoured vehicles ashore in the first 48 hours. German armoured reserves in France numbered fewer than 1,400 tanks and assault guns total, dispersed across hundreds of kilometres. The disparity grew more severe through June and July. Allied logistics chains delivered replacement vehicles, spare parts, fuel, and ammunition at rates German defenders could not match. When the 21st Panzer Division lost 15 tanks in combat on June 10, those losses were permanent. When British and American armoured divisions lost similar numbers, replacement vehicles arrived within 3 days. The Kummersdorf evaluation had predicted this scenario. Sherman reliability proved decisive in sustained operations. Allied armoured units maintained 70 to 80% operational readiness throughout the campaign, despite continuous combat. German panzer divisions struggled to keep 50% of their strength operational due to mechanical failures, parts shortages, and damage accumulation. Combat reports from Panzer Lehr Division, one of Germany's elite armoured formations, documented the pattern. On June 12, the division engaged Allied armour near Villers-Bocage. German tanks achieved favourable kill ratios, approximately 2.3 enemy vehicles destroyed for each German loss, but the division withdrew due to fuel shortages and mechanical breakdowns. Allied units absorbed their losses, received reinforcements, and continued offensive operations. By July, German commanders recognized that individual technical superiority no longer mattered. A Tiger tank could defeat 3 Shermans in direct combat, but 6 Shermans would arrive before the Tiger received fuel or ammunition resupply. Panthers outranged Shermans significantly, but Panther mechanical reliability averaged only 40% operational readiness, while Sherman formations maintained 75% availability. The simplicity and standardization that German engineers had noted at Kummersdorf proved strategically decisive. Allied maintenance units could swap Sherman engines in 4 hours using standard tools. Tracks, transmissions, and suspensions were interchangeable between vehicles. Parts arrived from depot stocks reliably. German tank crews might wait weeks for specialized components while their vehicles sat immobile. One German tank commander, Hauptmann Klaus von Rosen of the 12th SS Panzer Division, wrote in his combat journal on July 18, "We destroy their tanks effectively. They bring more tanks. We wait for parts. They repair and return. Our individual superiority is meaningless against their systematic advantages." The Normandy campaign confirmed every conclusion from the 1943 evaluation. The Sherman was not individually exceptional, but it was systematically unstoppable. American industrial capacity, manufacturing efficiency, and logistical organization had created a military advantage that German technical sophistication could not overcome. The war was effectively over. By year's end 1944, the production disparity had become catastrophic for Germany. American factories delivered 17,565 Sherman tanks that year. Soviet plants produced 14,648 T-34s. British production added 4,100 various tank types. Combined Allied output, approximately 36,000 tanks. Germany manufactured 8,328 tanks and assault guns in 1944 across all types: Panthers, Tigers, Panzer IVs, Sturmgeschütz. Even this figure, representing Germany's maximum industrial effort, barely exceeded 1/4 of Allied production. The 5-to-1 production advantage identified at Kummersdorf had become a reality. Battlefield mathematics followed industrial arithmetic. On the Western Front, Allied armoured divisions deployed approximately 11,000 tanks by December 1944. German forces in the West fielded roughly 1,500 operational tanks. On the Eastern Front, Soviet armoured and mechanized corps operated over 15,000 tanks. German Eastern forces mustered approximately 3,800 operational tanks and assault guns. The Wehrmacht faced a 2-front tank deficit exceeding 8-to-1. No amount of tactical skill or technical superiority could compensate for that numerical disadvantage. German armoured units won engagements but lost campaigns. They destroyed enemy tanks efficiently but could not prevent enemy advances. They demonstrated tactical excellence while suffering strategic collapse. Maintenance and logistics data from December 1944 revealed the cascading effects of industrial inadequacy. German armoured divisions reported average operational readiness of 35 to 40%. Fewer than half their authorized strength was combat capable at any time due to mechanical failures, parts shortages, and battle damage accumulation. Allied armoured formations maintained 70 to 75% operational readiness, despite continuous combat operations. The Sherman's greatest strength, identified at Kummersdorf 18 months earlier, had become Germany's primary weakness. Simplicity enabled mass production. Standardization enabled reliable logistics. Adequate performance enabled sustained operations. The Allied tank fleets were not individually superior, but they were systematically overwhelming. Intelligence reports reaching Berlin in late 1944 confirmed that Allied production would accelerate further in 1945. American factories were projected to produce 20,000 Shermans. Soviet production would reach 15,000 T-34s. British output would continue at 4,000 to 5,000 units annually. Germany's projected 1945 production, 6,000 tanks if strategic bombing didn't intensify, and material supplies remained adequate. Neither assumption was realistic. A strategic assessment prepared by the Wehrmacht High Command in December 1944 acknowledged the inevitable conclusion. We cannot win a war of attrition against opponents who outproduce us by factors of 5 to 10. Each engagement consumes irreplaceable resources. Each Allied loss is replaced within days. The numerical disparity renders tactical success strategically meaningless. The Kummersdorf evaluation had identified this outcome in 1943. The data, the analysis, and the conclusions had been clear, but awareness without adaptation was insufficient. Germany knew it could not compete industrially with the Allies. It simply had no means to change that reality. The end was now only a matter of time. On May 10, 1945, Soviet forces occupied Kummersdorf 3 days after Berlin's surrender. Engineers from the Red Army's Automotive Research Branch surveyed the testing grounds, workshops, and document archives. They discovered extensive technical files on captured Allied equipment, British Cromwells, American half-tracks, and detailed evaluations of the M4 Sherman. The Kummersdorf Sherman itself had disappeared. Records indicated it was moved to a storage depot in late 1944 as Allied bombing threatened the facility. Whether it was destroyed, abandoned, or lost in the wars, final chaos remained undocumented. The vehicle that German engineers had tested so thoroughly simply vanished into the collapse of the Third Reich. But the reports survived. American intelligence officers from the United States Strategic Bombing Survey recovered Wehrmacht technical files during Operation Paperclip operations in late 1945. Among thousands of documents, they found Heereswaffenamt files 26/43 and 41/43, the complete Kummersdorf Sherman evaluation, compiled by Karl Decker and his team. The files were classified and transferred to Aberdeen Proving Ground in Maryland for review by United States Army Ordnance. American engineers read German assessments of their own tank with professional interest. The evaluation was thorough, objective, and technically sound. German engineers had identified the Sherman's weaknesses accurately: thin side armor, high profile, limited gun penetration, but they had also recognized its systematic strengths: reliability, maintainability, production efficiency. One American engineer reviewing the documents noted in his analysis, "They understood the Sherman better than we expected. They recognized that we built it for mass production and sustained operations, not individual technical superiority. They saw the strategy embedded in the design." The documents remained classified until 1973, when the National Archives began declassifying Second World War technical intelligence. Historians examining the files recognized their significance. They documented the moment when German engineers understood with precision and clarity that industrial capacity would decide the war's outcome. The Kummersdorf evaluation documented a principle that extended beyond the Sherman tank itself. In industrial warfare, adequate systems produced in quantity defeat, superior systems produced in scarcity. Germany had optimized for quality. America had optimized for quantity. The strategic equation favored quantity when the quality gap remained narrow. The Sherman was never the best tank of World War II by any technical metric. It was outgunned by German Panthers and Tigers, less armored than Soviet IS-2s, less mobile than British Cromwells in certain conditions. Yet it became the most successful Allied tank because it combined adequate capability with overwhelming availability. By war's end, the United States had produced 49,234 Sherman tanks in all variants. The Soviet Union manufactured over 84,000 T-34s. Germany produced approximately 25,000 tanks total across all types from 1939 to 1945. The production disparity was fundamental and decisive. German engineering excellence produced remarkable vehicles. The Tiger's 88mm gun could destroy any Allied tank at ranges exceeding 2,000 meters. The Panther's sloped armor and high-velocity gun made it perhaps the finest medium tank design of the war. But Germany built 1,347 Tigers and 6,000 Panthers. America built nearly 50,000 Shermans. Excellence could not overcome insufficiency. The files from Kummersdorf captured this realization in real-time German engineers discovering that their opponents had mastered a different kind of warfare. The final paragraph of Decker's June 1943 report stated, Der Sherman demonstriert ein Prinzip, das der deutschen Fertigung unbekannt ist, Genügsamkeit durch Vereinfachung. The Sherman demonstrates a principle unfamiliar to German manufacture sufficiency through simplification. In the end, the most valuable result from the Kummersdorf tests was not mechanical but strategic, proof that wars of industry are won not by perfection but by production. Germany learned this lesson through careful analysis and systematic testing. They learned it accurately and completely. They learned it too late to change the outcome. What is your perspective on this part of history? Share your thoughts in the Miter's Eye Peep. Comments, because every memory and reflection helps keep the past alive.